Have you ever wondered that when you look up at the sky at night, you are actually looking through a time machine? That star you see shining today might have already vanished millions of years ago. We humans are not just figures of clay. We are star stuff. The iron flowing through our veins and the calcium in our bones were born from the death of a star. Today, we begin a journey that starts from Earth and travels to the very edge of the universe, where time and space cease to exist. Get ready to hear the saga of the stars. Stars are born in the vast, cold reaches of space within massive clouds of dust and gas known as nebulae. These stellar nurseries consist primarily of hydrogen, the simplest and most abundant element in the universe. The process begins when a disturbance, perhaps the shock wave from a nearby supernova or a galactic collision, causes the cloud to collapse under its own gravity. As the gas clusters together, it begins to spin and heat up, forming a dense core known as a protostar. For millions of years, gravity continues to pull material inward, increasing the pressure to unimaginable levels. Once the core temperature hits approximately 15 million degrees Celsius, a magical moment occurs. Nuclear fusion ignites. This is the official birth of the star. From this point on, the star is no longer just a collapsing cloud. It is a radiant engine of light and heat. This delicate dance between the inward pull of gravity and the outward push of nuclear energy defines the star's entire existence. Every star we see tonight was once part of a silent, dark nebula, transformed by the relentless power of gravity into a glowing beacon. The secret to a star's long life lies in its core, where a process called nuclear fusion serves as its primary power source. Unlike a fire on Earth that requires oxygen to burn, a star burns by fusing atoms together. Under extreme heat and pressure, hydrogen atoms collide with such violence that they overcome their natural repulsion and fuse into helium. This reaction releases a staggering amount of energy in the form of gamma rays and neutrinos. This energy travels from the core to the surface, eventually escaping into space as the light and heat we feel on Earth. Without this internal pressure, a star would collapse instantly under its own massive weight. Therefore, a star exists in a state of hydrostatic equilibrium, a permanent tug-of-war between gravity trying to crush the star and fusion trying to blow it apart. This process is so efficient that a star like our Sun can continue fusing hydrogen for 10 billion years. Humans are currently attempting to replicate this star power on Earth through fusion reactors, hoping to provide the world with a nearly limitless source of clean energy. While stars may appear as simple white dots in the night sky, they actually come in a diverse palette of colors that reveal their true nature. A star's color is a direct indicator of its surface temperature, following the laws of physics known as blackbody radiation. Contrary to our everyday intuition where red means hot and blue means cold, in the cosmos, the rules are reversed. The coolest stars in the universe are red dwarfs, with surface temperatures ranging from 2,500 degrees Celsius to 3,500 degrees Celsius. Our Sun is a medium-temperature yellow dwarf, sitting at about 5,500 degrees Celsius. The true titans of heat are the blue giants, which can reach blistering temperatures of over 30,000 degrees Celsius. These colors tell us how fast a star is burning through its fuel. Blue stars are high-energy gas guzzlers that live fast and die young, often in just a few million years. Red stars, however, are the frugal citizens of the galaxy, burning their fuel so slowly that they can live for trillions of years. By simply looking at a star's color, astronomers can determine its age, lifespan, and chemical composition. To understand the size of the largest stars, we must first realize how small we are. Our Sun is so large that it could hold 1.3 million Earths inside it. However, compared to a hypergiant like Stephenson 2 to 18, our Sun is like a single grain of sand next to a beach ball. Stephenson 2-18 is currently the largest known star, with a radius roughly 2,150 times that of the Sun. If you were to replace our Sun with Stephenson 2-18, its surface would extend past the orbit of Saturn, swallowing Mercury, Venus, Earth, Mars, and Jupiter in the process. If you wanted to fly a commercial airplane around its circumference, the journey would take you nearly 1,100 years, whereas circling the Earth takes only 40 hours. These stars represent the absolute limit of how large a star can grow before it becomes unstable. They are incredibly rare and usually short-lived, as their massive size causes them to shed their outer layers rapidly before ending their lives in spectacular supernova explosions. They serve as a humbling reminder of the sheer scale and grandeur of the universe we inhabit. Red dwarfs are the most common type of star in the Milky Way, making up about 75% of all stellar objects. Yet not a single one is visible to the naked eye from Earth because they are so dim. These stars are small, usually between 7% and 50% of the Sun's mass. Because of their low mass, the pressure in their cores is relatively low, which means they fuse hydrogen into helium at an incredibly slow and steady pace. While a massive blue star might burn out in a few million years, a red dwarf can keep its fire lit for trillions of years. In fact, the universe is currently about 13.8 billion years old, which means no red dwarf has ever died of old age yet. They are the ultimate survivors. As they age, they don't expand into red giants like our Sun. Instead, they simply become bluer and eventually fade into blue dwarfs and then white dwarfs. They are also prime candidates for finding alien life, as their long lifespans give biology billions of extra years to evolve on surrounding planets. However, they are prone to violent solar flares that could strip a planet's atmosphere, making the search for life around them a complex scientific debate. A supernova is the colossal explosion of a star, marking one of the most energetic events in the known universe. This happens when a massive star, at least 8 times the mass of our Sun, runs out of nuclear fuel. Without the outward pressure of fusion to hold it up, gravity wins the tug-of-war instantly, causing the star's core to collapse in less than a second. This collapse creates a shockwave that blows the star's outer layers into space at speeds of up to 30,000 kilometers per second. For a few weeks, a single supernova can outshine an entire galaxy containing billions of stars. These explosions are not just beautiful, they are essential for our existence. The intense heat of a supernova creates heavy elements like gold, silver, and uranium, scattering them across space to be recycled into new planets and eventually, living beings. If you are wearing a gold ring, that gold was forged in the heart of a dying star billions of years ago. A supernova is the universe's way of recycling. Death for one star means the birth of the building blocks for everything else. When a massive star goes supernova, the core that remains is sometimes crushed into a neutron star. Imagine the entire mass of our Sun, which is 330,000 times heavier than Earth, being squeezed into a sphere only the size of a small city, about 20 kilometers in diameter. This makes neutron stars the densest objects in the universe that we can actually see. The gravity on a neutron star is 2 billion times stronger than gravity on Earth. If you were to take just 1 teaspoon of neutron star material, it would weigh about 1 billion tons, roughly the weight of Mount Everest. Because they are so dense and have so much angular momentum, they spin incredibly fast. Some, known as pulsars, rotate hundreds of times per second, emitting beams of radiation like a cosmic lighthouse. These stars are so extreme that the mountains on their surface are only a few millimeters high, because the gravity is so strong that any taller structure would be instantly crushed flat. They represent the final boundary of matter before it collapses completely into a black hole. While our Sun sits solo in the center of our solar system, it is actually in the minority. Roughly half of all stars in the Milky Way are part of binary systems, where 2 stars orbit a common center of mass. Some systems are even more crowded, with 3, 4, or even 6 stars dancing around each other in complex gravitational loops. In a binary system, if the stars are close enough together, the more massive star can actually act like a vampire, using its gravity to suck the gas away from its smaller companion. This leads to fascinating visual possibilities. If you lived on a planet orbiting a binary system, you would see 2 suns in the sky, much like the fictional planet Tatooine in Star Wars. You would have 2 shadows, and depending on the orbits, you might never experience a truly dark night. These systems are crucial for astronomers because watching how 2 stars pull on each other allows us to calculate their masses with incredible precision. Without binary stars, our understanding of stellar weight and gravity would be far more limited. Looking at the stars is the closest thing we have to a real lifetime machine. Light is the fastest thing in the universe, traveling at 300,000 kilometers per second. But the universe is so vast that even light takes time to travel between points. When you look at the sun, you are seeing it as it was 8 minutes and 20 seconds ago. When you look at Proxima Centauri, the nearest star after the sun, you are seeing light that started its journey 4.2 years ago. This effect becomes mind-blowing when we look at distant stars in other galaxies. Some of the stars we see in the night sky may have already exploded or died thousands of years ago, but because they are so far away, the news of their death, conveyed by light, hasn't reached Earth yet. We are effectively looking at a ghost. The further into space we look, the further back in time we see. This allows telescopes like the James Webb to look at the very first stars that formed after the Big Bang, giving us a live look at the history of our universe's creation. When a star like our sun reaches the end of its life, it doesn't go out with a violent bang. Instead, it sheds its outer layers and leaves behind its core. This remnant is known as a white dwarf. A white dwarf is roughly the size of Earth but contains the mass of an entire sun. It is a retired star. It no longer performs nuclear fusion. It glows only because of the leftover heat from its previous billions of years of activity. Imagine a glowing charcoal ember in a fireplace after the fire has gone out. That is a white dwarf. It is so dense that a piece of it the size of a matchbox would weigh as much as an elephant. Over trillions of years, these stars will eventually cool down until they no longer emit heat or light, turning into theoretical objects called black dwarfs. However, because the universe is only 8 billion years old, it hasn't existed long enough for any white dwarf to cool down into a black dwarf yet. Our own sun is destined for this fate in about 5 billion years, ending its journey as a silent, Earth-sized diamond in the sky. We have all grown up singing "Twinkle, Twinkle, Little Star," but in reality, stars do not twinkle at all. If you were standing on the moon or the International Space Station, stars would appear as steady, unmoving points of light. The twinkling effect, scientifically known as stellar scintillation, is caused entirely by Earth's atmosphere. As the light from a star enters our atmosphere, it passes through different layers of air with varying temperatures and densities. These layers act like a series of moving lenses, refracting, bending the light in different directions millions of times per second. By the time that light reaches your eye, it is zigzagging slightly, making it appear to change position or brightness. This is also why planets don't usually twinkle. Because they are closer, they appear as tiny disks rather than pinpoints, and the atmospheric distortion isn't enough to make the entire disk shimmer away. For astronomers, this twinkling is actually a nuisance, which is why they build telescopes on high mountains or launch them into space to get above the blur of our air. Space is generally a place of predictable orbits, but some stars are on a one-way trip out of their galaxies. These are called hypervelocity stars. These stars travel at incredible speeds, sometimes over 3 million kilometers per hour. This is fast enough to overcome the gravitational pull of the entire Milky Way galaxy. How does a star get kicked out of its home? Usually, it's the result of a violent gravitational encounter. Most often, this happens when a binary star system, two stars orbiting each other, wanders too close to the supermassive black hole at the center of the galaxy. The black hole's intense gravity captures one star but slingshots the other away at extreme speeds, much like a stone from a catapult. These stars are destined to spend eternity traveling through the dark, empty void of intergalactic space, far away from any galaxy. They are the lonely travelers of the cosmos, carrying the secrets of the galactic center into the infinite unknown. If you thought a regular neutron star was extreme, meet the magnetar. A magnetar is a type of neutron star with a magnetic field so powerful it defies imagination. Their magnetic fields are approximately 1 quadrillion times stronger than Earth's. To put that in perspective, if a magnetar were located halfway between the Earth and the Moon, its magnetic pull would be strong enough to strip the data from every credit card on Earth and literally pull the iron atoms out of your blood. These stars are active and dangerous. Sometimes, the crust of a magnetar undergoes a starquake, similar to an earthquake. This shifting of the star's surface releases a burst of gamma rays and X-rays so intense that even if the star is tens of thousands of light years away, the radiation can physically affect Earth's upper atmosphere. They are the most magnetic objects ever discovered, and they challenge everything we know about how matter behaves under the influence of extreme physical forces. One of the most poetic facts about stars is that they are our literal ancestors. During the Big Bang, the universe was filled with only hydrogen, helium, and a tiny bit of lithium. There was no carbon for our DNA, no oxygen for us to breathe, and no iron for our blood. These elements did not exist until the first stars were born. Inside the high-pressure pressure cookers of stellar cores, simpler atoms were fused into heavier ones. When these stars died and exploded as supernovae, they scattered these newly created elements across the universe. Eventually, these bits of star dust gathered together to form our sun, our Earth, and eventually us. Every atom in your left hand probably came from a different star than the atoms in your right hand. As the astronomer Carl Sagan famously said, "We are made of star stuff." We are not just in the universe, we are a part of the universe that has developed a way to look back at itself and wonder about its origins. There is a fundamental limit to how massive a star can actually be, a boundary known as the Eddington limit. You might wonder, why can't a star just keep growing forever by sucking up more gas? The answer lies in the battle between light and gravity. As a star becomes more massive, its core becomes hotter and the nuclear fusion becomes more intense. This produces a massive amount of radiation pressure, literally the force of light pushing outward. If a star exceeds approximately 150 to 200 times the mass of our sun, the outward pressure of its own light becomes stronger than the inward pull of its gravity. At this point, the star literally blows itself apart, stripping away its outer layers into space. This is why we don't see stars that are millions of times heavier than the sun. The Eddington limit acts as the universe's cosmic police, enforcing a maximum weight capacity for stars. It ensures that the most brilliant stars are also the most unstable, living life on the edge of self-destruction. Not all stars shine with a steady, constant light like our sun. Some stars, known as variable stars, actually breathe or pulsate. Their brightness changes over periods of hours, days, or even years. The most famous of these are the Cepheid variables. These stars physically expand and contract. As they grow larger, they become dimmer and cooler, and as they shrink, the pressure builds up, making them hotter and brighter. This pulsation is more than just a cosmic quirk. It is a standard candle that allows us to measure the size of the universe. In the early 20th century, Henrietta Swan Leavitt discovered that the timing of a Cepheid's pulse is directly related to its true brightness. By measuring how fast a star beats, astronomers can calculate exactly how far away it is. This is how Edwin Hubble proved that the Andromeda Galaxy was a separate system and that our universe is expanding. These beating stars are the cosmic rulers that we use to map the vast darkness between the galaxies. In the cosmic hierarchy, there is a strange category of objects that are too big to be planets but too small to be stars. These are called brown dwarfs, often nicknamed failed stars. To be a true star, an object must have enough mass to create the pressure needed to fuse hydrogen into helium. Brown dwarfs fall just short of this threshold. They typically have a mass between 13 and 80 times that of Jupiter. While they can't fuse ordinary hydrogen, they can fuse a rare form of it called deuterium. Because of this, they glow very dimly with a dull red or magenta hue and eventually cool down over time. Brown dwarfs are fascinating because they often have weather just like planets. Astronomers have detected massive storms, clouds made of hot sand, and even rain made of molten iron on these objects. They represent the bridge between the world of planets and the world of stars, blurring the lines of how we define objects in the universe. A star does not just give off light. It also exhales a constant stream of particles known as solar wind. This wind is a plasma consisting of electrons, protons, and alpha particles that are ejected from the star's upper atmosphere at speeds of up to 900 kilometers per second. This wind creates a giant bubble in space called the heliosphere, which protects our solar system from the harsh radiation of deep interstellar space. When the solar wind from our sun hits Earth's magnetic field, it creates the beautiful auroras, the northern and southern lights. However, solar winds can also be destructive. If a star's wind is too strong, it can strip away the atmosphere of any nearby planets, leaving them as barren, airless rocks. This is likely what happened to Mars. As its internal magnetic field died, the solar wind slowly peeled away its atmosphere over billions of years. A star's wind is its invisible hand, shaping the habitability of every world that dares to orbit it. The very first stars to ever shine in the universe are known as population 3 stars, and they are the ultimate ghosts of astronomy. These stars were born about 100 million years after the Big Bang in a universe that contained absolutely no metals or heavy elements, only hydrogen and helium. Because there were no heavy elements to help the gas clouds cool down, these first stars had to be absolutely enormous, likely hundreds or even thousands of times more massive than our sun. They were incredibly bright, incredibly hot, and they lived very short lives, perhaps only a few million years before exploding as hypernovae. No human has ever seen a population 3 star because they all died out billions of years ago, but their legacy is everywhere. Their explosions seeded the universe with the very first heavy elements, allowing the next generation of stars, population 2 and our own population 1 sun, to form. They were the pioneers that brought an end to the cosmic dark ages and set the stage for the complex universe we live in today. When the most massive stars in the universe die, they don't just leave behind a dense core. They collapse so completely that they vanish from the visible universe, creating a black hole. At the center of this collapse is a singularity. But the most terrifying part is the event horizon. This is the invisible boundary surrounding the black hole where the escape velocity exceeds the speed of light. Once an atom, a beam of light, or a spaceship crosses this line, it is gone forever. No information can ever leak back out to tell us what is inside. Imagine a waterfall so powerful that no boat can row fast enough to go back up once it hits the edge. That is the event horizon. It represents a glitch in the fabric of space-time where the laws of physics as we know them break down. If you were to watch someone fall toward an event horizon from a distance, time would appear to slow down for them due to gravitational time dilation. You would see them freeze at the edge, slowly turning red and fading away, while from their perspective, they would fall right through into the unknown. It is the ultimate no trespassing sign of the cosmos. If you were to approach a stellar mass black hole, you would experience a gruesome phenomenon known as spaghettification. This is caused by extreme tidal forces. Gravity weakens with distance, but near a black hole, that change happens so rapidly over a short space that the pull on your feet would be millions of times stronger than the pull on your head, assuming you are falling feet first. The result is that your body would be stretched out like a piece of dough or a long strand of spaghetti. At the same time, the intense gravitational curvature would compress you from the sides. You would be narrowed and lengthened into a thin string of atoms before you even reached the event horizon. Interestingly, this only happens with smaller black holes. If you fell into a supermassive black hole, like the one at the center of our galaxy, the event horizon is so large that the tidal forces are much gentler, and you might actually survive the fall past the horizon, at least for a few seconds, before meeting the singularity at the center. It is a bizarre reality where being bigger actually makes the monster less immediately lethal. Every major galaxy, including our own Milky Way, hides a monster at its heart. Our central resident is Sagittarius A*, pronounced Sagittarius A star. It is a supermassive black hole with a mass of about 4 million suns. Although we cannot see the black hole itself, we know it is there because we can see stars whipping around an invisible point at millions of miles per hour. These stars, called S-stars, behave like a cosmic ballet being performed around a ghost. Sagittarius A* is relatively quiet compared to black holes in other galaxies, but it is the gravitational anchor that holds the central core of our galaxy together. In 2022, the Event Horizon Telescope gave us the first ever direct image of the glowing gas surrounding this dark giant, proving that the math Einstein proposed over a century ago was correct. It sits 26,000 light-years away, a silent, dark sun around which our entire galactic neighborhood rotates. It is the ultimate reminder that even the brightest galaxies are built around a foundation of total darkness. While black holes themselves are dark, the areas immediately surrounding them can be the brightest spots in the universe. As a black hole's gravity pulls in nearby gas and dust, the material doesn't fall straight in. It spirals around like water going down a drain, forming an accretion disk. Because of the extreme gravity, this material orbits at significant fractions of the speed of light. The friction and collisions between these particles generate temperatures of millions of degrees. This heat causes the disk to glow brilliantly in X-rays and visible light. In galaxies where the central black hole is feeding heavily, these disks become so bright they are called quasars. A quasar can be 1,000 times brighter than the entire Milky Way galaxy, even though it is only about the size of our solar system. It is one of the universe's great ironies. A black hole, the symbol of darkness, can power the most luminous light bulbs in existence. These accretion disks are essentially cosmic power plants, converting the potential energy of gravity into raw radiation. Stars don't just exist in flat disks. Some are packed into tight, spherical swarms called globular clusters. A single cluster can hold up to 1 million stars in a space only a few dozen light-years across. If you lived on a planet inside a globular cluster, the night sky would be so crowded with stars that you could read a book by their light alone. There would be no true darkness, only a sky filled with thousands of suns as bright as the full moon. These clusters are some of the oldest structures in the universe, containing stars that are nearly as old as the Big Bang itself. They act as time capsules, preserving the history of how galaxies first formed. Because the stars are so close together, they often collide or interact, creating strange objects like blue stragglers, stars that look young but are actually old stars that have merged to gain a second life. They are the crowded, ancient cities of the cosmos, floating in the outskirts of galaxies like sparkling diamonds. For centuries, humanity wondered if our sun was the only star with a family of planets. In 1992, we finally got our answer. The universe is teeming with worlds. These are called exoplanets. As of now, we have confirmed over 5,000 of them, ranging from rocky super-Earths to hot Jupiters, giant gas planets that orbit so close to their stars that their years last only a few hours. Finding these planets is an incredible feat of engineering because stars are so bright that their light completely drowns out the dim reflection of a planet, like trying to see a firefly hovering next to a searchlight from miles away. Most exoplanets are found using the transit method. When a planet passes in front of its star, it causes a tiny temporary dip in the star's brightness, sometimes by less than 1%. By measuring the timing and depth of these dips, astronomers can calculate the planet's size, its orbit, and even the composition of its atmosphere. We have discovered worlds where it rains glass sideways, planets made largely of diamond, and water worlds covered by oceans hundreds of miles deep. The diversity of these worlds proves that our solar system is just one of many possible blueprints in the stellar architecture of the galaxy. One of the most important concepts in the study of stars and planets is the habitable zone, often called the Goldilocks zone. This is the region around a star where the temperature is just right, not too hot that water boils away, and not too cold that it stays frozen as ice. Since liquid water is the essential ingredient for life as we know it, finding planets in this zone is the ultimate goal of modern astronomy. The distance of this zone depends entirely on the type of star. For a hot, blue star, the habitable zone is very far away. For a small, cool red dwarf, the zone is so close that the planet might be tidally locked, meaning one side always faces the star, permanent day, and the other always faces away, permanent night. Finding a planet like Earth around a star like our Sun is like looking for a needle in a cosmic haystack. But we have already found several Earth cousins that might have the right conditions for life. The search for a second Earth is a search for our own place in the grand narrative of the stars. If you look at the periodic table, almost every element you see was cooked inside the heart of a star through a process called stellar nucleosynthesis. In its early life, a star fuses hydrogen into helium. As it ages and gets hotter, it begins to fuse helium into carbon and oxygen. In its final massive stages, it fuses elements all the way up to iron. This is the absolute limit for a normal star. Fusing iron consumes more energy than it produces, leading to the star's inevitable collapse. This means that stars are the ultimate chemists. Without them, the universe would be a boring soup of simple gases. Every bit of gold in your jewelry, every breath of oxygen in your lungs, and every calcium atom in your teeth was once forged in the crushing heat of a star's core. We are the survivors of ancient cosmic explosions. When we study the chemical makeup of a star today, we are actually reading its DNA to see what generation it belongs to and how many previous stars had to die to provide the materials for its birth. It is a cycle of life, death, and rebirth on a galactic scale. To our eyes, the constellations look permanent. The Big Dipper looks the same today as it did to the ancient Egyptians. However, this is an illusion caused by the vast distances of space. In reality, every star is moving at tens of thousands of miles per hour. This movement is known as proper motion. Over tens of thousands of years, the shapes of the constellations will warp and change beyond recognition. Barnard's star is the speed demon of our neighborhood. It moves across the sky faster than any other star, covering a distance equal to the diameter of the full moon every 180 years. Most stars orbit the center of the Milky Way just like planets orbit a star. Our sun is currently traveling at 450,000 miles per hour, yet even at this breakneck speed, it takes 230 million years to complete just one trip around the galaxy. The last time the sun was in its current position in the Milky Way, dinosaurs were just starting to roam the Earth. The night sky is not a static painting. It is a high-speed highway where everything is in constant, silent motion. Galaxies are not isolated islands. They often interact and even eat each other in a process called galactic cannibalism. When a large galaxy like the Milky Way gets close to a smaller satellite galaxy, its gravity begins to tear the smaller one apart, stripping away its stars and gas. We can actually see stellar streams in our own galaxy, trails of stars that used to belong to other galaxies but were stolen by the Milky Way billions of years ago. In about 4 billion years, the Milky Way will undergo its most famous collision with the Andromeda Galaxy. Despite having billions of stars each, the space between stars is so vast that it is highly unlikely any two stars will actually hit each other. Instead, they will pass by like ghosts, their gravity flinging them into new orbits. This collision will trigger a massive starburst, a period where thousands of new stars are born at once from the compressed gas. Eventually, the two will merge into one giant elliptical galaxy, often nicknamed Milkdromeda. It is a violent but creative process that ensures the universe never remains the same for long. How do we know what a star is made of if we've never been there? The answer lies in spectroscopy, the science of breaking down light into its component colors. When light from a star's core passes through its cooler outer atmosphere, the elements there absorb specific wavelengths of light. This creates a pattern of dark lines on a rainbow-colored background, known as an absorption spectrum. Each element, hydrogen, helium, iron, magnesium, leaves a unique fingerprint or barcode at specific points on that spectrum. By reading these barcodes, astronomers can tell you exactly what a star is made of, its temperature, its pressure, and even how fast it is rotating. We can even determine if a star is moving toward us or away from us using the Doppler effect. If a star is moving toward us, its light waves are compressed and shift toward the blue end of the spectrum, blue shift. If it is moving away, the waves stretch and shift toward the red shift. This cosmic forensic science allows us to understand the chemistry of a star trillions of miles away without ever leaving our planet. When you look at the Milky Way on a very dark night, you might notice dark, empty patches where no stars seem to exist. These aren't actually holes in space. They are dark nebulae. These are clouds of interstellar dust so dense and cold that they completely block the visible light from the stars behind them. One of the most famous examples is the Coalsack Nebula. To the naked eye, it looks like a terrifying void, but through an infrared telescope, these clouds become transparent. Infrared light has longer wavelengths that can tunnel through the dust particles. When we look at dark nebulae in infrared, we discover that they are actually the busiest places in the galaxy. Inside these dark, cold cocoons, gravity is quietly pulling gas together to create thousands of new stars. They are like cosmic curtains, hiding the construction zones of the universe. Without these dark clouds, the cycle of star birth would grind to a halt. They represent the quiet, invisible potential of the universe, where the next generation of suns is currently being forged in total darkness. Humans aren't the only ones who have used the stars to find their way. Evolutionary biology has revealed that several animal species have stellar navigation hardwired into their brains. For example, indigo buntings, a type of bird, learn the rotation of the night sky to identify the North Star, using it as a compass for their massive migrations. Even more fascinating is the dung beetle. Research has shown that these tiny insects use the soft glow of the Milky Way galaxy to roll their dung balls in a straight line, preventing them from accidentally circling back to competitors. If the stars were to suddenly vanish, these animals would lose their way. This connection suggests that stars have been shaping the behavior and evolution of life on Earth for millions of years. It's not just a matter of wonder. For many creatures, the stars are a survival tool. This biological link reminds us that we are part of a planet that is deeply integrated into the cosmic environment. Our relationship with the stars is etched into the very DNA of the life forms that share our world. One of the greatest unsolved mysteries in stellar physics is the coronal heating problem. Logic dictates that as you move away from a heat source, the temperature should drop. If you move your hand away from a campfire, it gets cooler. However, the sun defies this rule. The surface of the sun, the photosphere, is about 5,500 degrees Celsius, but the corona, the sun's wispy outer atmosphere, reaches temperatures of over 1 to 2 million degrees Celsius. Scientists are still trying to figure out exactly why this happens. The leading theories involve magnetic reconnection, where magnetic field lines snap and release energy, and nanoflares, billions of tiny explosions happening every second. During a total solar eclipse, when the moon blocks the main body of the sun, the corona becomes visible as a ghostly white halo. This crown of fire is a reminder that even the star we know best still holds secrets that challenge our understanding of thermodynamics. Every star has this mysterious, superheated atmosphere, acting as a chaotic boundary between the star and the vacuum of space. There is a cruel irony in the universe. The more fuel a star has, the shorter its life will be. This is known as the mass-luminosity relationship. A star with 10 times the mass of our sun doesn't live 10 times longer. It lives about 1,000 times shorter. This is because a massive star has much more gravity, which crushes the core with immense force. To prevent itself from collapsing, the star must burn its hydrogen fuel at a furious, desperate rate, creating incredible brightness but exhausting its supply in only a few million years. On the other hand, tiny red dwarfs have very little mass and very little gravity. They sip their fuel so slowly that they can remain stable for up to 10 trillion years, a time frame much longer than the current age of the universe. This means that in the far, far future, long after the sun and all the brilliant stars of the night sky have died, the universe will belong to the small, dim red dwarfs. They are the tortoises in the race against time, while the brilliant blue giants are the hares that burn out in a spectacular flash. We are all familiar with earthquakes, but did you know that stars experience their own version called starquakes? This phenomenon is most violent on neutron stars. Because a neutron star is so dense, it has a solid crust made of crystalline iron nuclei. As the star rotates and its magnetic field shifts, the crust can crack under the immense gravitational pressure. When this crust snaps, it releases a staggering amount of energy. A starquake of just a few millimeters on a neutron star can release more energy than all the nuclear weapons on Earth combined. In 2004, a massive starquake occurred on a magnetar, a highly magnetic neutron star located 50,000 light-years away. The blast was so powerful that it physically compressed Earth's upper atmosphere, even though it happened on the other side of the galaxy. By studying the rings or vibrations caused by these quakes, a field known as astroseismology, astronomers can actually see inside stars to understand their internal structure, much like geologists use earthquakes to map the interior of the Earth. In the complex math of general relativity, the same equations that predict black holes also suggest the existence of their opposites, white holes. While a black hole is a region of space where nothing can escape, a white hole is a region where nothing can enter. It is essentially a cosmic fountain that constantly ejects matter and light from its event horizon. For a long time, white holes were considered purely mathematical curiosities, but some modern physicists suggest they might be the exit point for matter that falls into a black hole, possibly connected by a bridge called a wormhole. Another theory suggests that the Big Bang itself might have been a massive white hole, a singular point that exploded with all the matter and energy in our universe. While we have never observed a white hole directly, they remain one of the most provocative hooks in stellar science, representing the possibility that every end in the universe, a black hole, might be a beginning somewhere else. When we think about stars, we think about the deadly radiation they emit: UV rays, X-rays, and gamma rays. However, life on Earth has produced a creature capable of surviving the harshest stellar environments: the tardigrade, or water bear. These microscopic organisms can survive in the vacuum of space, exposed to the direct radiation of the sun without any protection. Tardigrades achieve this by entering a state of cryptobiosis, where they dry out and stop their metabolism. In this state, they can survive temperatures near absolute zero and the intense heat of 150 degrees Celsius. Their ability to survive the space environment has led some scientists to consider the theory of panspermia, the idea that life could be hitched on asteroids or comets and travel from one star system to another. This biological hardiness suggests that the universe might not be as sterile as it seems. If a tiny creature from Earth can survive the radiation of a star, perhaps life is already thriving in the most extreme corners of our galaxy. One of the most dramatic events in the life of stars is when two ultradense remnants, like two neutron stars or two black holes, finally collide. As these giants orbit each other, they move closer and closer, spinning faster and faster. This movement creates ripples in the very fabric of space-time itself, known as gravitational waves. In 2015, the LIGO Observatory detected these ripples for the first time, confirming a prediction made by Albert Einstein 100 years prior. These waves are like cosmic sound. They allow us to hear the universe even when no light is produced. When neutron stars merge, they create a kilonova, an explosion that produces most of the universe's heavy elements like gold and platinum. This means that your wedding ring isn't just made of star stuff. It is the result of two dead stars smashing into each other at a fraction of the speed of light, sending ripples through the entire universe. Even stars and galaxies aren't just floating aimlessly. They are being pulled. Our Milky Way, along with thousands of other galaxies, is racing at 1.4 million miles per hour toward a mysterious point in space known as the Great Attractor. This region is located about 220 million light-years away, but we can't see exactly what it is because it is hidden behind the zone of avoidance, the thick dust of our own galaxy's disk. The Great Attractor is a massive concentration of mass so great that it exerts a gravitational tug over a region of space hundreds of millions of light-years wide. Some astronomers believe it is a supercluster of galaxies, while others think it might be something even more exotic. It acts as the stellar North Pole of our local universe, a silent gravity well that is slowly drawing in every star and planet in our vicinity. It is a reminder that in the cosmos, there is always a bigger force at play, and every star is part of a much larger, invisible flow. In the world of stars, death isn't always final. Some stars, specifically white dwarfs, can be brought back to life in a violent process known as a Type Ia supernova. This happens in a binary system where a dead white dwarf orbits a living, bloated star. The white dwarf, despite being dead, has immense gravity. It begins to feed on its companion, pulling hydrogen gas onto its surface. Once the white dwarf reaches a very specific mass, exactly 1.44 times the mass of our Sun, known as the Chandrasekhar limit, it can no longer support its own weight. Instead of collapsing into a black hole, the pressure triggers a runaway nuclear fusion reaction that blows the entire star apart. Because these explosions always happen at the exact same mass, they always produce the exact same brightness. This makes them standard candles for astronomers. By measuring how dim these zombie star explosions appear, we can calculate the distance to the furthest galaxies in the universe. They are the cosmic beacons that revealed the most shocking secret of all: that the expansion of the universe is actually accelerating. One of the most iconic images in the history of astronomy is the Pillars of Creation, located in the Eagle Nebula. These towering clouds of gas and dust are several light-years tall, so large that our entire solar system would be a tiny speck at the very tip of one finger. These pillars are stellar nurseries where new stars are currently being carved out of the cold interstellar medium. The pillars are shaped by photoevaporation. Nearby massive, hot stars emit intense ultraviolet radiation that acts like a cosmic wind, sandblasting the gas clouds and eroding them away. The denser pockets of gas resist this erosion, forming the pillars we see. Inside the tips of these pillars are EGGs, evaporating gaseous globules, which hide developing protostars. However, there is a haunting possibility. Because the Eagle Nebula is 7,000 light-years away, some astronomers believe a nearby supernova might have already knocked these pillars down 6,000 years ago. We are seeing a masterpiece that might already be a ruin, waiting for the light of its destruction to reach us. As we look toward the far future of humanity, scientists have theorized about stellar engines, megastructures designed to move an entire star system. Why would we want to move the sun? Perhaps to avoid a nearby supernova or to navigate our solar system away from a collision with another galaxy. One such theoretical design is the Shkadov thruster. A Shkadov thruster is a colossal, curved mirror placed on one side of a star. The mirror would reflect the star's radiation back toward it. The pressure from this reflected light would create a tiny amount of thrust. Over millions of years, this microscopic push would be enough to move the sun and all its orbiting planets out of their natural path. While this sounds like science fiction, it is grounded in the real physics of radiation pressure. It represents the ultimate level of stellar engineering, where a civilization stops being a victim of cosmic events and starts driving its own star through the galaxy. One of the strangest theoretical objects in the universe is the Thorn-Zitko object, TO. This is essentially a Russian nesting doll of stars. It forms when a red supergiant star swallows a nearby neutron star. Instead of the neutron star destroying the larger star, it sinks to the center and settles in the core. Usually, a star's core is powered by fusion. But in a TO, the core is a solid ball of neutrons. The energy is produced not by fusion, but by gravity as gas from the red giant falls onto the surface of the neutron star. From the outside, it looks like a normal red supergiant, but its chemical signature is unique. It would contain unusually high levels of elements like rubidium and molybdenum. In 2014, astronomers discovered a star, HV 2112, that appears to be the first ever candidate for a TO. It is a reminder that the universe can create hybrids that challenge our basic definitions of what a star is supposed to be. If you want to understand the biography of every star in the sky, you need the Hertzsprung-Russell HR diagram. This is a graph that plots stars based on their brightness, luminosity, versus their temperature, color. When you plot thousands of stars on this map, they don't appear randomly. They fall into distinct patterns that reveal their age and fate. Most stars, including our sun, fall along a diagonal line called the main sequence. This is the adult phase of a star's life. When stars run out of fuel, they move off this line, moving toward the top right to become red giants or crashing down to the bottom left to become white dwarfs. The HR diagram is essentially the circle of life for the cosmos. It allows astronomers to look at a cluster of stars and tell you exactly how old it is and how much longer it has to live, simply by seeing where the stars are sitting on this cosmic map. We have discussed the supernova, but there is an even more terrifying older brother in the stellar family, the hypernova. These are explosions with more than 100 times the energy of a standard supernova. They occur when a star of extreme mass, up to 150 times that of our sun, collapses at the end of its life. Because these stars are often spinning at incredible speeds, the collapse creates a massive engine at the center, usually a black hole, which shoots out two narrow jets of plasma at nearly the speed of light. If one of these jets is pointed directly at Earth, we see it as a gamma ray burst, GRB. A GRB can release more energy in 10 seconds than our sun will emit in its entire 10 billion year lifetime. If a hypernova occurred within a few thousand light years of Earth, the radiation would strip away our ozone layer, causing a mass extinction. Fortunately, these monsters are rare and usually happen in very young, distant galaxies. They represent the absolute limit of stellar violence, turning a single star into a beacon that can be seen across the entire observable universe. Looking trillions upon trillions of years into the future, physics predicts a strange state for the remnants of stars, the iron star. Currently, stars fuse light elements into heavier ones. In a very distant future, after all the stars have stopped shining and the universe has become cold and dark, a slow process called quantum tunneling might take over. Over timescales so long they are hard to write in numbers, roughly \BM, 10 carat, 1,500 years, even the cold atoms in a dead star might slowly fuse into iron. Iron is the most stable nuclear configuration. Therefore, every cold, dead sphere of matter might eventually turn into a sphere of pure, solid iron. These iron stars would be perfectly cold, dark, and silent, floating through a universe that has expanded so much that no other objects are visible. They represent the ashes of the universe. However, even these might not last forever. If protons eventually decay, as some theories suggest, these iron stars will slowly evaporate into a mist of subatomic particles, leaving the universe truly empty. Our solar system is like a crime scene, and the suspects are ancient stars that died long before Earth was born. By studying meteorites, rocks that have existed since the birth of our solar system, scientists can perform interstellar archaeology. Inside these rocks, we find tiny pre-solar grains. These are microscopic diamonds and dust particles that were forged in the atmospheres of red giant stars and the debris of supernovae billions of years ago. By analyzing the isotopes in these grains, we can tell exactly what kind of stars were in our neighborhood before the sun formed. We have discovered that a nearby supernova likely triggered the collapse of the gas cloud that became our sun. This means we aren't just made of star stuff. We are the product of a specific cosmic event. Our solar system is the graveyard of a previous generation of stars, and every planet is built from the recycled wreckage of stars that lived and died in this very spot billions of years ago. One of the most famous sites in the universe is the Pillars of Creation in the Eagle Nebula. These towering clouds of interstellar gas and dust are several light years tall. While they look like solid mountains, they are actually translucent and ghostly. They are shaped by photoevaporation. The intense ultraviolet light from nearby young, hot stars acts like a cosmic wind, eroding the cloud and sculpting it into long pillars. Inside these pillars, new stars are being born. The denser pockets of gas act as shields, protecting the protostars growing inside them. However, there is a tragic irony to this beauty. Because the Eagle Nebula is 7,000 light years away, we see it as it was 7,000 years ago. Some astronomers believe a supernova shockwave already passed through this region 6,000 years ago, knocking the pillars down. We might be looking at a ghost of a masterpiece that has already been destroyed, waiting for the light of that destruction to finally reach Earth. We usually think of stars as being part of a galaxy, but there are millions of rogue stars drifting in the intergalactic void, the empty space between galaxies. These stars were once part of a galaxy but were violently ejected. This can happen during a galactic collision, or if a star passes too close to a supermassive black hole and gets slingshot away at millions of miles per hour. These stars are the ultimate loners. If a rogue star has planets, the night sky for those worlds would be pitch black. There would be no Milky Way, no constellations, and no other stars. Just one lonely sun in an infinite, dark ocean. Some estimates suggest there could be as many rogue stars as there are stars inside galaxies. They are a reminder that the universe is not just a collection of neat, organized islands of light, but also contains a vast, invisible population of wanderers lost in the dark. In the ancient, crowded environments of globular clusters, stars don't always follow the standard rules of aging. Astronomers often find stars that appear much younger, hotter, and bluer than they should be, considering the age of the cluster. These are known as blue stragglers. For a long time, they were a mystery. It was as if someone had found a teenager living in a retirement home. We now know that these stars are the vampires of the cosmos. Blue stragglers form through two violent methods: direct collisions or mass transfer. In a crowded cluster, two stars can physically slam into each other, merging their fuel to create a new, more massive star. Alternatively, in a binary system, a smaller star can slowly suck the outer layers off its aging companion. This fresh influx of hydrogen fuel allows the vampire star to restart nuclear fusion at a higher rate, making it look young and blue again. They are a stark reminder that in the crowded parts of the universe, a star's life can be extended through the destruction of its neighbor. Stars are not just balls of gas. They are massive balls of plasma, which is gas that has been ionized so it can conduct electricity. Because stars rotate and have internal convective currents, hot gas rising, cool gas sinking, they act like giant dynamos, generating incredibly powerful stellar magnetic fields. These invisible lines of force govern almost all the weather we see on a star. When magnetic field lines become twisted and tangled due to the star's rotation, they can snap and reconnect, releasing massive amounts of energy in the form of solar flares and coronal mass ejections, CMEs. These fields also create sunspots, cooler, darker regions where the magnetic field is so strong that it prevents hot gas from rising to the surface. Without these magnetic fields, stars would be much quieter, but they would also lack the solar wind that helps shape the protective bubbles around their planetary systems. The magnetic field is the invisible nervous system of a star, reacting to every internal pulse. When we look out from our position in the Milky Way to study other stars and galaxies, we hit a major problem. Our own galaxy gets in the way. This region is called the zone of avoidance. Because the disk of the Milky Way is filled with thick clouds of interstellar dust and millions of stars, it acts like a fog that blocks our view of about 20% of the extragalactic sky. For decades, this was a massive blind spot in our map of the universe. We knew there were massive structures out there, like the Great Attractor, but we couldn't see them in visible light. Modern astronomy has found a workaround using radio waves and infrared light, which can pass through the dust like X-rays through skin. By looking through our own galaxy, we've discovered thousands of hidden galaxies and massive walls of stars that were previously invisible. It is a humbling fact that even while we study the furthest reaches of the cosmos, our own home galaxy is the biggest obstacle to our vision. The birth of a star is not a quiet event. It is a violent, high-energy process. As a protostar forms within a collapsing nebula, it is surrounded by a spinning disk of gas and dust. Not all of this material falls into the star. Some of it gets caught in the star's powerful magnetic fields and is funneled toward the poles. From there, it is blasted into space in the form of protostellar jets. These jets can stretch for light years and travel at hundreds of kilometers per second. When they slam into the surrounding gas of the nebula, they create glowing knots known as Herbig-Haro HH objects. These jets act like a cosmic exhaust system, carrying away excess angular momentum so the star can finish collapsing. To an observer, these jets look like massive beams of light shooting out of a dark cloud, a spectacular announcement that a new sun has finally ignited in the darkness. The very first stars in the universe were giants made only of hydrogen and helium, known as population 3 stars. But their impact was much bigger than just providing the first light. Before these stars existed, the universe was filled with a neutral fog of hydrogen gas that blocked light. This period is known as the cosmic dark ages. When the first population 3 stars ignited, their intense ultraviolet radiation was so powerful that it began to ionize the surrounding gas, stripping the electrons off the hydrogen atoms. This process is called reionization. It effectively cleared the fog, making the universe transparent for the first time. Without these first short-lived monsters, the universe would have remained a dark, opaque soup. They were the cosmic architects that turned on the lights and allowed the universe to become the vast, transparent theater of galaxies and stars that we see today. Deep in the constellation of Centaurus lies a cosmic treasure that sounds like a fairy tale, a star made of diamond. This object, officially named BPM 37093, is a white dwarf, the compressed corpse of a star that was once very similar to our sun. As a star like this dies, it leaves behind a core made mostly of carbon and oxygen. For decades, theorists predicted that as these cores cooled, the intense pressure would cause the carbon to crystallize. In 2004, astronomers confirmed that BPM 37093 has indeed crystallized, creating a diamond stone that is 4,000 kilometers in diameter. To put that in perspective, that is a diamond larger than the moon, weighing approximately 10 billion trillion carats. Astronomers nicknamed the star Lucy as a tribute to the Beatles' song Lucy in the Sky with Diamonds. It is a staggering reminder that the extreme physics of space can turn the common elements of life into the most precious structures imaginable. One day, trillions of years from now, our own sun will undergo this same transformation, ending its life as a cold, silent diamond drifting through the dark. While we think of tsunamis as massive waves of water on Earth, the sun experiences its own version on a much grander and more terrifying scale. These are called Moreton waves, or solar tsunamis. They are not made of water, but of hot, magnetized plasma and shock waves. These waves are triggered by massive explosions on the sun's surface, such as a coronal mass ejection, CME, or a powerful solar flare. When one of these explosions occurs, it sends a ripple across the sun's surface, the chromosphere, that travels at speeds of up to 1,000 kilometers per second. A single solar tsunami can rise to heights of 100,000 kilometers, enough to swallow dozens of Earths, and can travel across the entire diameter of the sun in just a matter of minutes. These waves carry enough energy to disrupt the magnetic fields of the entire solar system. By studying how these waves move, scientists can map the invisible magnetic topography of the sun, much like geologists use seismic waves to map the interior of our planet. We have touched on brown dwarfs as failed stars, but their atmospheres are among the strangest places in the universe, because they are much cooler than regular stars. Some are even as cool as a cup of hot coffee. They allow for complex chemistry that would be impossible in a hotter sun. In these in-between worlds, the temperatures are just right for minerals to condense into clouds. Astronomers have used infrared telescopes to detect weather patterns on brown dwarfs that would seem like a nightmare to us. In the upper atmospheres of these objects, it literally rains molten iron. As the heat from the core rises, iron vapor condenses into liquid droplets that fall through the clouds, only to evaporate again as they hit the hotter layers below. Some brown dwarfs even have clouds made of silicates, hot sand, or rubies and sapphires. They are the ultimate hybrid objects, possessing the mass of a giant planet but the turbulent, fiery atmosphere of a dying star. Our sun is not a static object. It goes through a violent mood swing every 11 years known as the solar cycle. This cycle is driven by the sun's magnetic field, which gets twisted and tangled as the sun rotates. The equator rotates faster than the poles. During solar minimum, the sun is quiet and has very few sunspots. But as the cycle progresses toward solar maximum, the magnetic activity peaks, leading to massive flares and disruptions that can knock out satellite communications on Earth. The most incredible part of this cycle happens at the peak. The sun's magnetic poles actually flip. The North Pole becomes the South Pole and vice versa. It's as if Earth's compasses suddenly pointed toward Antarctica. This magnetic reset clears the tangled field lines and starts the process all over again. This cycle has been happening for billions of years, and by studying the rings of ancient trees on Earth, we can actually see the fingerprints of these 11-year solar cycles dating back thousands of years, showing how deeply our planet's history is tied to the heartbeat of its star. When a star dies and becomes a black hole or a neutron star, it often begins to feed on a nearby companion star. As the gas is pulled toward the collapsed object, it doesn't fall straight in. It forms a spinning flat disk called an accretion disk. Because of the extreme gravity, the gas in the inner parts of the disk orbits much faster than the gas in the outer parts. This creates incredible friction. The gas particles rub against each other at significant fractions of the speed of light, heating the disk to millions of degrees. This friction is so efficient that it converts mass into energy much more effectively than nuclear fusion. While fusion in a star converts about 0.7% of mass into energy, an accretion disk around a spinning black hole can convert up to 42% of mass into energy. This makes accretion disks the most efficient power plants in the universe, emitting brilliant X-rays that can be detected from across the galaxy, revealing the location of otherwise invisible dark stars. A star is not a silent, static ball of light. It is a violent engine that exhales a constant stream of high-energy particles known as stellar winds. These winds consist of electrons, protons, and alpha particles ejected from the star's outer atmosphere, the corona, at speeds reaching up to 900 kilometers per second. While we cannot see this wind with our eyes, its impact is felt throughout the entire solar system. It is the force that pushes the tails of comets away from the sun, ensuring they always point outward regardless of which way the comet is traveling. For a star, these winds are a form of weight loss. Our sun loses about 1 billion kilograms of material every second through solar wind. While that sounds like a lot, the sun is so massive that it has only lost about 0.5% of its total mass over the last 4.5 billion years. However, in more massive, hotter stars, stellar winds can be so powerful that they strip away the star's entire outer envelope, exposing its naked core. These winds also create a protective bubble called the heliosphere, which acts as a shield, blocking dangerous cosmic rays from the deep galaxy from entering our planetary neighborhood. Every star has a territory that extends far beyond its visible planets. For our sun, that territory ends at the Oort cloud. This is a theoretical, gargantuan shell of billions of icy objects that surrounds the solar system at a distance of nearly 2 light-years, almost halfway to the next star. The Oort cloud is essentially a deep freezer of ancient history, containing the leftover building blocks from the formation of the solar system 4.6 billion years ago. The objects in the Oort cloud are so far from the sun that they are barely held by its gravity. Every once in a while, a passing star or a galactic tidal force nudges one of these icy rocks, sending it tumbling toward the inner solar system. When it gets close to the sun's heat, it begins to melt and grow a glowing tail, becoming a long-period comet. This cloud defines the gravitational border of our star. Beyond this point, the sun's influence fades, and the vast, empty ocean of interstellar space begins. We often think of the space between stars as a vacuum, but it is actually a rich laboratory for complex chemistry. In the cold, dark regions of interstellar clouds, atoms of hydrogen, carbon, oxygen, and nitrogen collide and bond. Because the temperatures are so low, near absolute zero, these chemical reactions happen very slowly, but over millions of years, they create complex molecules. Astronomers using radio telescopes have detected over 200 different types of molecules in these clouds, including water, ammonia, and even complex organic compounds like formaldehyde and ethyl alcohol. Most importantly, we have found prebiotic molecules, the precursors to amino acids, which are the building blocks of life. This means that the seeds of life aren't just found on planets. They are manufactured in the freezing voids of space, long before a star or a planet is even born. We are the result of a chemistry that began in the dark, silent gaps between ancient suns. People often confuse solar flares with coronal mass ejections, CMEs, but they are distinct types of stellar outbursts. A solar flare is a sudden, intense burst of radiation light caused by the snapping of magnetic field lines, travels at the speed of light and reaches Earth in just over 8 minutes. While it can disrupt radio communications, it is mostly a light show. A CME, however, is much more physical. It is a massive burp where the star flings billions of tons of actual plasma, electrically charged gas, into space. This plasma travels much slower, taking 1 to 3 days to reach Earth. When a CME hits our planet, it triggers a geomagnetic storm. While this creates stunning auroras, it can also induce massive electrical currents in our power grids, potentially blowing out transformers and plunging entire continents into darkness. In 1859, a massive CME known as the Carrington event was so powerful that telegraph wires caught fire and people could read newspapers by the light of the aurora in the middle of the night in the Caribbean. If you look at a high-resolution photo of the sun, you'll notice that the edges of the disk appear darker than the center. This phenomenon is called limb darkening. It is not an optical illusion. It provides a deep look into the structure of a star's atmosphere. When we look at the center of the sun, our line of sight goes straight down into the deeper, hotter, and brighter layers of the photosphere. However, when we look toward the limb, the edge, our line of sight passes through the atmosphere at an angle, meaning we are only seeing the higher, cooler, and therefore dimmer layers. This effect allows astronomers to calculate the temperature gradient of a star, essentially mapping how fast the temperature drops as you move from the core to the surface. It is a reminder that a star isn't a solid ball with a hard surface. It is a translucent, layered sphere of gas where the edge is simply the point where the gas becomes too thin for us to see through. What happens when a star gets too close to a supermassive black hole? It undergoes a violent death known as a tidal disruption event, TDE. As the star approaches the black hole, the gravitational pull on the side of the star nearest the black hole is significantly stronger than on the far side. This creates tidal forces so intense that they overcome the star's internal gravity. Instead of being swallowed whole like a marble, the star is literally ripped apart into a long, thin stream of gas. This process is called spaghettification on a stellar scale. About half of the star's debris is flung away into deep space at incredible speeds, while the other half spirals back toward the black hole, forming a temporary, ultra-bright accretion disk. This disk glows brilliantly in X-rays, acting as a flare that alerts astronomers to a black hole that was previously sitting in total darkness. It is a rare, spectacular way for a star to end its life, not with a bang, but by being shredded into a ribbon of light. How do we know the distance to a star if we can't fly there with a tape measure? We use a technique called stellar parallax. You can experience this yourself. Hold your finger in front of your face and close one eye, then the other. Your finger appears to jump against the background. Astronomers do the same thing, but instead of using 2 eyes, they use the Earth's orbit. By taking a picture of a star in January and another in July, we are viewing it from 2 points 300 million kilometers apart. The star appears to shift slightly against the distant, fixed background of further galaxies. By measuring this tiny angle, which is often smaller than the width of a human hair seen from a mile away, we can use basic trigonometry to calculate the exact distance to the star. This was the first method ever used to prove that stars aren't just points on a ceiling, but distant suns separated by trillions of miles of empty void. For a long time, scientists thought that supernovae created all the heavy elements. However, modern physics revealed a problem. Even a supernova isn't quite energetic enough to create the massive amounts of gold, platinum, and uranium we find in our solar system. The real alchemy happens during a kilonova. A kilonova occurs when two neutron stars, the ultra-dense remnants of dead giants, collide. As they spiral into each other, they smash together at nearly the speed of light. The resulting explosion is 1,000 times brighter than a standard nova. In the extreme heat of this collision, neutrons are shoved into atomic nuclei at a blistering rate, creating the heaviest elements in the universe. In 2017, astronomers detected one of these collisions and calculated that it produced a mass of gold equivalent to several times the mass of the Earth. This means every piece of gold jewelry you own was forged in a collision so violent it shook the very fabric of space-time. While we focus on stars, the emptiness between them is equally fascinating. Astronomers have discovered regions of the universe known as supervoids, and the most famous is the Eridanus supervoid, or the CMB cold spot. This is a vast region of space, roughly 1 billion light-years across, that contains significantly fewer stars and galaxies than the rest of the universe. It is like a massive hole in the cosmos. Some theories suggest this void is simply a natural variation in the density of the early universe, but more radical theories suggest it could be a bruise, where our universe bumped into another bubble universe in a multiverse. Because there are so few stars inside the void to provide light or heat, the cosmic microwave background radiation in that direction is slightly colder. If you were in a spaceship in the middle of this void, the night sky would be almost entirely black, with the nearest stars so far away they wouldn't even be visible to the naked eye. We often draw stars as perfect spheres, but stars are actually fluid-like bodies made of plasma, and their rotation changes their shape. Because of centrifugal force, stars that spin quickly tend to bulge at the equator and flatten at the poles. This shape is known as an oblate spheroid. Our sun is almost a perfect sphere because it rotates slowly, once every 27 days. However, a star like a Kerner spins so fast at 250 kilometers per second that its equatorial diameter is 50% wider than its polar diameter. If you looked at it, it would look like a flattened beach ball. This rapid spinning also creates a phenomenon called gravity darkening, where the equator of the star is cooler and dimmer than the poles because it is further away from the hot core. It is a reminder that stars aren't solid objects. They are dynamic, spinning oceans of fire that are physically reshaped by the laws of motion. While globular clusters are ancient and crowded, open clusters represent the youth of the galaxy. These are groups of a few dozen to a few hundred stars that were all born from the same giant molecular cloud at roughly the same time. Because they share the same parentage, they all have a similar chemical composition and age. The most famous example is the Pleiades, or the Seven Sisters, which is easily visible to the naked eye. Unlike globular clusters, which stay together for billions of years, open clusters are loosely bound by gravity. As they orbit the center of the galaxy, the gravitational tides from other stars and gas clouds slowly pull them apart. Over a few 100 million years, the cluster dissolves, and the stars go their separate ways to become lonely travelers like our sun. In fact, our sun was likely born in an open cluster 6 billion years ago, surrounded by hundreds of sibling stars. Today, those siblings are scattered across the Milky Way, and astronomers are currently searching for these solar twins to better understand our own star's history. We often think of light as something that just illuminates, but light actually carries momentum. This discovery has led to the concept of solar sails, a method of spacecraft propulsion that uses the radiation pressure from a star to move. Just as a sailboat is pushed by the wind, a solar sail is a giant, ultra-thin mirror that is pushed by the constant stream of photons, light particles, hitting its surface. While the push from light is incredibly small, roughly equivalent to the weight of a postage stamp on a football field, in the vacuum of space it is constant. Since the spacecraft doesn't need to carry any heavy fuel, it can keep accelerating as long as the star is shining. Over months and years, a solar sail could reach speeds far beyond any chemical rocket. Japan's Ikaros and the LightSail 2 projects have already proven this works. For future interstellar travel, we could even use giant lasers to blast these sails, potentially reaching the nearest stars within a human lifetime. It is the ultimate green energy for the space age. Space is not a perfect vacuum. It is filled with tiny particles of silicates, graphite, and ice known as interstellar dust. When light from a distant star travels through this dust, it undergoes a process called extinction. The dust particles are just the right size to scatter and block shorter wavelengths of light, blue and violet, while letting longer wavelengths, red and infrared, pass through. This creates a phenomenon called interstellar reddening. A distant star will appear redder and dimmer than it actually is, much like how the sun looks red during a sunset because its light is passing through more of Earth's atmosphere. If astronomers didn't account for this cosmic fog, they would incorrectly calculate a star's temperature and distance. By studying this reddening, we can actually map the location and density of the dust clouds in our galaxy, turning a nuisance into a tool for understanding the dark architecture of the Milky Way. How does a star go from fusing helium to creating the carbon that makes up your body? It's not as simple as two atoms hitting each other. It requires a rare and delicate nuclear dance called the triple alpha process. In the late stages of a star's life, the core becomes incredibly hot and dense. Two helium nuclei, alpha particles, fuse to form beryllium-8. However, beryllium-8 is extremely unstable and usually decays back into helium in a fraction of a second. For carbon to form, a third helium nucleus must hit that beryllium-8 atom almost instantly before it disappears. This triple collision creates a stable carbon-12 nucleus. This process is so specific and unlikely that it has been called a cosmic miracle. If the laws of physics were even slightly different, this process wouldn't work, and the universe would be filled with helium but have no carbon, no oxygen, and no life. Every carbon atom in the universe is a survivor of this high-speed, three-way collision that happened inside a dying red giant billions of years ago. Measuring the universe is like building a ladder. Each rung depends on the one below it. The first rung is stellar parallax. As Earth orbits the Sun, nearby stars appear to shift slightly against the background of much more distant stars. By measuring this tiny angle, astronomers can use simple trigonometry to calculate the distance to that star. However, parallax only works for stars within a few thousand light-years. To go further, we use the standard candle method, such as Cepheid variable stars. Because we know exactly how bright a Cepheid star should be based on its pulse rate, we can compare that to how dim it looks to find its distance. This ladder continues to type Ia supernovae and eventually to the expansion of the universe itself. Without the first simple step of parallax, the shift of a star in our sky, we would have no way of knowing if the universe was a few miles wide or billions of light years across. Every object in the universe has a theoretical limit known as the Schwarzschild radius. This is the radius to which an object must be compressed for its escape velocity to equal the speed of light, effectively turning it into a black hole. For our Sun, that radius is approximately 3 kilometers. If you could somehow crush the entire mass of the Sun into a sphere the size of a small town, it would become a black hole. For the Earth, the Schwarzschild radius is roughly the size of a marble, 9 millimeters. This concept, named after physicist Carl Schwarzschild, defines the event horizon. It is the mathematical boundary where space and time switch roles. Once a star collapses within this radius, the paths leading away from the center literally cease to exist in the geometry of space. It is not just that gravity is strong. It is that the fabric of reality has curved so sharply that every possible future direction for a particle points toward the central singularity. This radius represents the ultimate point of no return for matter and energy. When a supermassive black hole at the center of a galaxy begins to feed on stars and gas, it creates a quasar. These are the most luminous objects in the universe. A quasar is powered by an accretion disk that is trillions of times more energetic than our sun. As matter is pulled toward the black hole, it is heated to millions of degrees by friction and magnetic forces. Quasars are so bright that they can be seen from the very edge of the observable universe, billions of light years away. In fact, a single quasar can emit 1,000 times more light than all the hundreds of billions of stars in the Milky Way galaxy combined. They were much more common in the early universe when galaxies were younger and had more fuel for their central black holes. Today, most quasars have gone quiet as their black holes have finished their meal, but their light still travels across space, telling us the story of a violent, high-energy era when the first galaxies were still finding their shape. One of the deepest mysteries in stellar and black hole physics is the black hole information paradox. According to the laws of quantum mechanics, information, the specific state of every atom and particle, can never be truly destroyed. However, general relativity suggests that if a star falls into a black hole, all information about that star, its mass, its temperature, its composition, is lost to the rest of the universe, leaving only its mass, charge, and spin. This creates a massive conflict in modern physics. If information is destroyed, then the foundations of quantum physics are wrong. If it is saved, we don't know how it gets out. Stephen Hawking later proposed that black holes might slowly evaporate through Hawking radiation, and that the information might be encoded in this radiation, much like the data on a hard drive that has been burned to ash. Solving this paradox is the holy grail of modern science, as it would finally unite the world of the very large, stars, with the world of the very small, atoms. Just as archaeologists dig through layers of Earth to find ancient civilizations, astronomers use stellar archaeology to find the first generation of stars. We do this by looking at a star's metallicity. In astronomy, any element heavier than hydrogen and helium is called a metal. The very first stars, population 3, had 0 metals. When they exploded, they seeded the next generation, population 2, with a tiny bit of metal. Our sun is a population 1 star, meaning it is metal-rich because it was born from the wreckage of many previous generations. By searching for ultrametal-poor stars in the outskirts of our galaxy, we are essentially looking at living fossils. These stars have been shining since nearly the beginning of time. Finding a star with almost no metal content allows us to see exactly what the universe was like 13 billion years ago, providing a direct link to the chemistry of the Big Bang itself. When we look at light from incredibly distant quasars or stars, we often see a forest of absorption lines in their spectra. This is known as the Lyman alpha forest. Each tree in this forest represents a cloud of neutral hydrogen gas that the light passed through on its multi-billion-year journey to Earth. By analyzing these lines, astronomers can map the cosmic web, the invisible structure of the universe where galaxies and stars are born. The Lyman alpha forest shows us the state of the gas between stars across different eras of cosmic time. It tells us when the first stars began to reionize the universe and clear the fog of the dark ages. It is the ultimate shadow play, where the light of a distant star reveals the presence of invisible gas clouds that haven't been seen for billions of years. Just as white dwarfs have a weight limit, Neutron stars have their own line in the sand, known as the Tolman-Oppenheimer-Fokoff (TOV) limit. This limit represents the maximum mass a neutron star can have before the pressure of its own neutrons can no longer withstand the crushing force of gravity. Currently, this limit is believed to be around 2.1 times the mass of our Sun. If a neutron star gains even a fraction of mass beyond this point, perhaps by colliding with another star or sucking gas from a companion, it will instantly lose its battle with gravity. The star will vanish from the visible universe, collapsing inward to form a black hole. This limit is the ultimate tipping point of physics. It defines the boundary between the densest form of observable matter and the mysterious, invisible singularity where matter as we know it ceases to exist. In the complex dance of binary star systems, there is an invisible boundary shaped like a figure eight called the Roche lobe. Each star has its own sphere of influence, where its gravity is dominant. However, if one star begins to expand, as our Sun will do when it becomes a red giant, its outer layers can cross this boundary and fall into the Roche lobe of its companion. This is the start of stellar cannibalism. The companion star begins to strip mine the larger star, pulling a stream of hot plasma across the gravitational bridge. This mass transfer can completely change the fate of both stars. The vampire star gains mass and can become a supernova, while the victim star is stripped down to its naked, glowing core. It is a reminder that in the crowded parts of the galaxy, the life and death of a star are often dictated by the proximity of its neighbors. While we focus on individual stars, every sun in the sky is part of a massive, invisible flow. Our Milky Way is part of a continent of galaxies called Laniakea, which contains over 100,000 galaxies. All of these galaxies, and every star within them, are being drawn toward a mysterious gravitational center known as the Great Attractor. This isn't a single object like a giant star, but a massive concentration of mass located 220 million light-years away. Because it lies in the zone of avoidance, the area hidden by our own galaxy's dust, we cannot see it directly. We only know it exists because we can see the currents of galaxies flowing toward it. It is the ultimate destination for our stellar neighborhood, a silent, invisible force that reminds us that even the most brilliant stars are just grains of sand in a much larger cosmic river. As we look forward trillions of years, we enter the degenerate era. This is a time when the universe has stopped making new stars because it has run out of gas. The only objects left are the corpses of stars, white dwarfs, neutron stars, and black holes. During this era, the universe will look nothing like it does today. There will be no brilliant constellations or glowing nebulae. Instead, the sky will be filled with cold, dark spheres that slowly cool down toward absolute zero. If a white dwarf and a neutron star happen to collide, they might create a brief, final flash of light, but for the most part, the universe will be a silent graveyard. This era lasts for an incomprehensible amount of time, /BM, 10 40 years, representing the long, slow cooling of the cosmic fire that began with the Big Bang. In the ultimate reach of time, physics suggests the existence of iron stars. Over unimaginable timescales, quantum tunneling will cause the atoms in dead stars to slowly fuse into iron, the most stable element. But even these eternal iron spheres might have an end. If the theory of proton decay is correct, the very atoms that make up these stars will eventually dissolve. After /BM 10 100 years, the iron stars will evaporate into subatomic particles, and even the largest black holes will have disappeared due to Hawking radiation. At this point, the universe enters the dark era. There will be no stars, no matter, and no heat. Just a thin, infinite mist of photons and electrons in a universe that has reached total equilibrium. This heat death is the final chapter of the stellar story. The stars were a brief, brilliant moment of light and complexity in a universe that spent most of its life in the dark. We are lucky enough to exist in that tiny window of time where the lights are still on. We know that when a star collapses, it can become a neutron star, a city-sized ball of neutrons. But some physicists believe there is a state of matter even denser than that, quark matter. If the pressure inside a neutron star is high enough, the neutrons themselves might dissolve into their constituent parts, up, down, and strange quarks. This would create a quark star. A quark star would be even smaller and denser than a neutron star, and it might be composed of strange matter. The terrifying thing about strange matter is that it is theorized to be the most stable state of matter in the universe. Some strange-let theories suggest that if a piece of strange matter ever touched ordinary matter, like an atom from our sun or Earth, it would instantly convert that matter into more strange matter. This would trigger a chain reaction that could turn an entire planet or star into a lump of strange quarks in seconds. While purely theoretical, quark stars represent the absolute limit of what solid matter can be before it surrenders to the gravity of a black hole. Stars and galaxies don't just sit in space. They warp it. Because mass curves space-time, a massive object like a cluster of stars can act as a giant lens. This is known as gravitational lensing. When light from a very distant galaxy passes near a closer, massive star or galaxy, the light is bent around it, just like light passing through a glass lens. This effect allows astronomers to see objects that would otherwise be far too dim or distant to detect. Sometimes, this lensing creates Einstein rings, perfect circles of light, or Einstein crosses, where the same distant object appears 4 times around the foreground lens. By studying these distorted images, we can calculate the mass of the lens star, even if it is a dark object like a black hole. It is a cosmic trick that lets us use the stars themselves as a telescope to look deeper into the history of the universe. There is a controversial and fascinating theory called stellar metamorphosis, which suggests that planets are not formed from a disk of dust around a star, but are actually the final stage of a star's life. According to this idea, as a star cools down and loses its outer layers of plasma, it slowly transitions into a gas giant, like Jupiter, then eventually cools further into a rocky, differentiated world, like Earth. While the mainstream nebular hypothesis, planets forming in disks, is the accepted model, the study of hot Jupiters and brown dwarfs has shown us that the line between a large planet and a small star is incredibly blurry. Whether or not Earth was once a star, the chemistry of our world, the iron in our core and the gases in our atmosphere, is undeniably stellar in origin. Every world we walk upon is, at the very least, the ash of a long-dead stellar fire that if a star orbits a spinning black hole, it enters a region called the ergosphere. This is a part of space-time that is literally being dragged around by the black hole's rotation. Physicist Roger Penrose theorized that a civilization, or even a natural phenomenon, could use this area to steal energy from the black hole. This is called the Penrose process. In this scenario, an object like a piece of a star enters the ergosphere and splits in two. One half falls into the black hole, while the other half is flung out at a much higher speed than it entered. The extra energy comes from the black hole's own rotational momentum. Over time, this would actually slow down the black hole's spin. It is the ultimate form of energy extraction, using the leftovers of a star to tap into the power of a gravitational giant. It proves that even in death, a star's remnants can be used to fuel the most energetic processes in the cosmos. Just as there is a habitable zone around a star, there is likely a galactic habitable zone. Not all stars are in a good place for life. Stars near the center of the galaxy are too crowded. The frequent supernovae and intense radiation from the central black hole would likely sterilize any planets nearby. Conversely, stars at the very edge of the galaxy are metal poor, meaning they lack the heavy elements, like iron and silicon, needed to build rocky planets like Earth. Our Sun is located in the Goldilocks part of the Milky Way, far enough from the center to avoid radiation, but close enough to have plenty of heavy elements. This galactic geography suggests that the story of life is not just about having the right star, but about that star being in the right neighborhood. As we map the billions of stars in our galaxy, we aren't just looking for suns. We are looking for the quiet, stable corners of the universe where the star stuff had enough time and peace to become something more complex. Among the rarest theoretical objects in the cosmos is the Thorn-Zitko object, TO. This occurs when a red supergiant star swallows a neutron star. Instead of the neutron star destroying its host, it sinks to the very center and becomes the core. This creates a star within a star. Unlike a normal star powered by nuclear fusion, a TO is powered by the gravitational energy of gas falling onto the neutron star's surface. From the outside, it looks like a standard red giant, but its chemical signature is unique, containing unusually high amounts of rubidium and lithium. In 2014, astronomers discovered a candidate star named HV 2112 in a neighboring galaxy that matches this profile. It represents a hybrid state of matter that challenges our fundamental understanding of how stars are powered, proving that the universe often finds ways to recycle the dead into something entirely new. How do we know a star is 100 light-years away versus 1,000? We use a method called stellar parallax. As the Earth orbits the Sun, nearby stars appear to shift slightly against the background of much more distant galaxies. It's the same effect you see when you look out a car window. The trees nearby move fast, while the distant mountains barely move. By measuring this tiny wobble over 6 months, astronomers can use basic trigonometry to calculate the exact distance to a star. This is the first rung on the cosmic distance ladder. Once we know the distance to a few nearby stars, we can use their brightness to calibrate standard candles like Cepheid variables and Type Ia supernovae to measure the distance to other galaxies. Without this simple geometric trick, our map of the universe would be a total mystery. We would be like sailors at sea with no way to tell how far away the shore is. In the far, far future, trillions of years after the last red dwarf has burned out, the universe enters a stage where matter itself begins to change. Through a process of quantum tunneling, the atoms in dead stars will slowly fuse until they all become iron. Iron is the most stable nuclear configuration. It is the bottom of the well for energy. These iron stars will be cold, black spheres of pure metal drifting through an empty, expanding void. However, even they might not be eternal. If proton decay is a reality, the very subatomic particles that make up the iron will eventually dissolve over a span of \BM 10 carat 100 years. The stars will slowly evaporate into a mist of light and electrons. This represents the final breath of the stellar era, where the solid remnants of the universe's greatest engines finally return to the vacuum from which they came. For most of human history, we saw the stars. But in 2015, we began to hear them. When two ultra-dense objects like black holes or neutron stars collide, they send ripples through the fabric of space-time itself. These are gravitational waves. These waves travel at the speed of light and physically stretch and compress everything in their path, including you. By the time they reach Earth, the movement is smaller than the width of a single proton, yet we have built machines, LIGO and Virgo, sensitive enough to detect them. This technology has opened a new window into the dark side of the universe. We can now study events that emit no light at all, listening to the shouts of dying stars as they merge into the darkness. It is a reminder that the stars are not just lights in the sky. They are physical powerhouses that shake the very foundation of reality. We end where we began, with the realization that there is no separation between the cosmos and yourself. The iron in your blood was forged in the final seconds of a massive star's life. The calcium in your bones was baked in a red giant. The gold in your jewelry was created when two dead suns collided. The universe spent 13.8 billion years cooking the atoms that currently make up your body. You are a way for the cosmos to know itself. When you look up at the night sky, you aren't looking at something outside of you. You are looking at your ancestors. The stars had to die so that you could live. In the grand script of the universe, the story of the stars is actually the story of us. Stars are not silent. They are constantly vibrating. Just as a bell rings when struck, a star rings due to the constant movement of hot gas rising and falling in its interior. This field of study is called astroseismology. These vibrations are essentially sound waves traveling through the star's plasma. While these sounds cannot travel through the vacuum of space to our ears, we can see them as tiny, rhythmic changes in a star's brightness. By analyzing these frequencies, astronomers can do something incredible. They can hear the internal structure of a star. Different sizes and ages of stars vibrate at different pitches. A massive red giant has a deep, bass-like thrum, while a small white dwarf has a high-pitched ring. This allows us to calculate a star's exact age, its density, and even the size of its core with unbelievable precision. It turns the night sky into a silent orchestra, where every point of light is playing its own unique, internal melody. The very first stars to ever ignite in the universe, known as population 3 stars, were unlike anything we see today. Because the early universe was made only of hydrogen and helium, these stars could grow to enormous sizes, potentially 300 to 1,000 times the mass of our sun. They were terrifyingly hot, brilliant, and short-lived. These stars were the pioneers. Their intense ultraviolet light ended the cosmic dark ages by ionizing the surrounding gas, making the universe transparent for the first time. They lived fast and died hard, exploding in hypernovae that seeded the universe with the very first heavy elements. Although no population 3 star exists today, their ghosts are still with us. Every atom of carbon or oxygen in your body can be traced back to the wreckage of these first ancient monsters that turned on the lights in a dark universe. Galaxies like our Milky Way have a respiratory system known as galactic fountains. When massive stars in the disk of the galaxy explode as supernovae, they blast enormous clouds of hot, enriched gas out of the galaxy's plane and into the halo, the space above and below the galaxy. As this gas travels into the cold halo, it eventually cools down and loses energy. Gravity then pulls it back down into the disk, like rain falling from a cloud. This recycled gas is filled with the heavy elements forged in those dying stars. When it hits the disk, it triggers the birth of new stars. This cycle ensures that each new generation of stars is more metal-rich than the last. Our own sun was likely born from the rain of a galactic fountain that occurred billions of years ago, proving that galaxies are living, breathing systems of recycled stellar matter. One of the most profound facts about studying stars is that we never see them as they are now. We only see them as they were. Because light travels at a finite speed, roughly 300,000 kilometers per second, it takes time to reach us. When you look at the sun, you see it as it was 8 minutes ago. When you look at Sirius, you see it as it was 8 years ago. This means that a telescope is actually a time machine. When we look at stars in distant galaxies, we are looking back millions or even billions of years into the past. We can literally see the universe being born. This look-back time is our only way to study the history of the cosmos. If a star 1,000 light-years away exploded tonight, we wouldn't know about it for another 10 centuries. We live in a universe of delayed news, where the night sky is a collection of ancient history reaching us at the speed of light. As we conclude these 100 points of light, we must acknowledge the cosmological principle. This is the starting point for all modern astronomy. It states that on a large enough scale, the universe is both homogeneous, it looks the same everywhere, and isotropic, it looks the same in every direction. This means that the laws of physics we discover here on Earth, the way gravity works, the way atoms fuse, the way light travels, apply to every star in every galaxy, no matter how far away. The universe is not a chaotic mess. It is a unified system. Whether a star is in the Milky Way or a galaxy 10 billion light-years away, it follows the same script. This unity is what allows us to sit on a small, rocky planet and claim to understand the hearts of giants and the birth of time itself. As a civilization grows, its energy needs eventually outpace what can be gathered from a single planet. Physicist Freeman Dyson theorized that an advanced Type II civilization might build a Dyson sphere. This is not necessarily a solid shell, but a gargantuan swarm of solar collectors, mirrors, and habitats that completely surround a star. By capturing 100% of the star's energy output, a civilization would have trillions of times more power than we currently use on Earth. While we haven't found a confirmed Dyson sphere yet, astronomers look for them by searching for stars that flicker strangely or emit an unusual amount of infrared waste heat. In 2015, a star named Tabby's star, KIC 8462852, gained worldwide fame because its light dimmed in a jagged, unpredictable way that some suggested could be a megastructure in progress. While most now believe it was cosmic dust, it sparked a new era of searching for the technological footprints of other civilizations among the stars. Deep inside the crust of a neutron star, matter is crushed so intensely that atoms lose their identity. This leads to the creation of nuclear pasta. At these extreme densities, the competition between the electrical repulsion of protons and the attractive strong nuclear force causes the matter to arrange itself into bizarre shapes. Physicists have named these shapes based on their resemblance to Italian food. You have gnocchi, blobs of protons and neutrons, spaghetti, long strings, and lasagna, flat sheets. This material is the strongest substance in the universe, roughly 10 billion times stronger than steel. To snap a single strand of nuclear pasta, you would need the energy of a supernova. It represents the final boundary of solid matter before gravity collapses everything into the mathematical point of a black hole. We usually learn about stars by looking at their light, but sometimes we learn the most by watching them disappear. This is called stellar occultation. It happens when a small, dark object, like an asteroid, a moon, or a distant planet, passes directly in front of a star. For a few brief seconds, the star's light blinks out. By timing how long the star is hidden and observing how the light fades at the edges, astronomers can measure the size and shape of the passing object with incredible accuracy. This technique was used to discover the rings of Uranus and to detect the thin atmospheres of distant moons like Pluto's Charon. It turns every star into a backlight that allows us to see the tiny, dark rocks drifting in the outer reaches of our solar system. In 1977, a radio telescope detected a powerful, narrowband signal coming from the direction of the constellation Sagittarius. It lasted for 72 seconds and was so unusual that the astronomer wrote, "Wow," on the printout. For decades, it was the best candidate for an extraterrestrial broadcast. Modern research has traced the signal's origin to a specific region of space near a sun-like star called 2MASS 1928198-2-2640123. While many scientists now believe the signal might have been caused by a passing comet's hydrogen cloud, the WOW signal highlights the importance of stellar context. We don't just look for life in the void. We look for it in the habitable neighborhoods of stars that match the temperature and stability of our own sun. The search for star stuff that has become intelligent is perhaps the most exciting chapter in all of astronomy. Most planets are found because they block a star's light, transits, or tug on the star, radial velocity. But there is a third, more Einsteinian way to find them: gravitational microlensing. This occurs when a distant star aligns perfectly with a closer star. The closer star acts as a lens, magnifying the light of the distant one. If the lens star has a planet orbiting it, that planet will create its own tiny blip in the magnification. This allows us to find planets that are thousands of light years away, far beyond the reach of other methods. It even allows us to find rogue planets that have been kicked out of their solar systems and are drifting in total darkness. By using the gravity of stars as a natural magnifying glass, we have discovered that planets are not the exception. They are a fundamental part of the stellar life cycle. While most stars in the Milky Way orbit the galactic center in a predictable circular path, there is a class of rebels known as hypervelocity stars. These stars travel at speeds exceeding 2 million miles per hour, fast enough to overcome the gravitational pull of the entire galaxy. They are literally being kicked out into the intergalactic void. This usually happens through a violent gravitational slingshot near the supermassive black hole at the center of our galaxy, Sagittarius A star. When a binary star system gets too close to the black hole, one star is captured and swallowed, while its partner is flung away at incredible velocity. These stars are the ultimate exiles. They will spend the rest of eternity traveling through the dark, empty space between galaxies, never to return home. They serve as a reminder that the heart of our galaxy is a place of extreme physics where even a sun can be treated like a pebble tossed into a pond. In our local universe, we see stars and galaxies everywhere. But there is a region of space known as the Boötes Void, or the Great Nothing, that defies all expectations. It is a spherical region of space roughly 330 million light-years in diameter that is almost entirely empty. According to standard models of the universe, a region this size should contain about 2,000 galaxies. Instead, we have found only about 60. If the Milky Way were in the center of the Boötes Void, we wouldn't have known there were other galaxies until the 1960s. The stars in this region are so isolated that the night sky, for any planets there, would be terrifyingly dark. Astronomers still struggle to explain how such a massive hole could form in the distribution of matter. Some suggest it was formed by smaller voids merging together like bubbles in a sink, while more fringe theories speculate it could be the result of an advanced civilization expanding so far that they have dimmed all the stars in the region. We often say we are made of star stuff, but the process, stellar nucleosynthesis, is a masterclass in nuclear engineering. Every star is a pressure cooker that fights a constant battle between the inward crush of gravity and the outward push of nuclear fusion. In its youth, a star fuses hydrogen into helium, but as it ages, it begins to cook heavier and heavier elements. Inside a massive star, layers form like an onion. The outer layer fuses hydrogen, the next fuses helium, then carbon, neon, oxygen, and silicon. Each stage happens faster and hotter than the last. The silicon burning stage, which creates iron, lasts for only 1 day before the star collapses. Because iron is the ash of nuclear fusion and cannot be fused to create more energy, the star's engine stalls. The resulting supernova explosion is what finally flings these cooked elements, the oxygen you breathe and the calcium in your teeth, out into the universe to be used in the next generation of life. One of the greatest mysteries in stellar physics is known as the lithium problem. According to our models of the Big Bang, the universe should have produced a specific amount of lithium. However, when we look at the oldest, most ancient stars in the galaxy, they contain significantly less lithium than our theories predict. Where did the lithium go? Some astronomers believe it is being destroyed inside the stars, while others think our understanding of the early universe's chemistry is flawed. Interestingly, some stars, known as lithium-rich giants, actually have more lithium than they should, suggesting they might have recently swallowed a planet. Lithium is a fragile element, easily destroyed by the heat of a star's interior, and its mysterious levels act as a cosmic chemical tracker that helps us understand the hidden mixing processes happening deep within a star's core. Just as we use ultrasound to look inside the human body, astronomers use helioseismology to look inside the sun. The sun is a resonant cavity filled with millions of sound waves, P-modes, caused by the turbulent movement of gas. These waves cause the surface of the sun to oscillate up and down in patterns that we can measure from Earth. By studying these vibrations, we have discovered that the sun's interior does not rotate like a solid ball. The equator rotates faster than the poles, and there is a specific layer called the tachocline where the rotation speed changes abruptly. This layer is believed to be the dynamo that generates the sun's massive magnetic field. Without helioseismology, the interior of our star would be as opaque as a stone wall. With it, we can see all the way down to the nuclear core, monitoring the heartbeat of the engine that sustains all life on Earth.